Okay, so the topic for today is EIGRP. Okay, so as we discussed in the previous class about a brief on routing, and after routing we checked a little bit on static routing and all other types of dynamic routings. Okay, so we were discussing about some dynamic routing like RIP, EIGRP, OSPF. Okay. So along with these, there is one more protocol which is called as EGP, which is Exterior Gateway Protocol, and the best example for this is BGP. Okay, so in the CCNP syllabus we have EIGRP and OSPF and BGP. Okay, we do not have RIP. Now, to someone who is joining for the first time, where are this routing protocol used? It's used to communicate between two different routers. Okay, so let's say you have a LAN network, okay, which consists of core, distribution and access layer. Okay, so let's say these are access layer which connects directly with the computers, and over here you have the distribution switches, and over here you have the core switches, a core router, and these are the core router which connects to ISP. So your packet will travel across the ISP, from one ISP to the second ISP, the third ISP, and then finally it will reach to the destination. Okay, so till here, access and distribution, it was more related to switching technology. Okay, it was more dealing with MAC address. But now, since we are talking about the core layers, it's all about routing technology, dealing with multiple networks. Okay, why do we call it as multiple network? Because these routers, okay, they will have individual networks on their interface. That means, let's say I have a router. Okay, so on a router's end, on a router interface, one interface will belong to one network. Similar way, let's say I have a another interface which is connecting to some other router or some other path. Okay, now that will be connected on a different network. Okay, whereas in switch can have all in same VLAN. Okay, I can have a switch configured in all in a single VLAN. Okay, but in the case of router, I cannot have two different interface participating on a single network. I cannot have this as 1.1.1.3. Okay, it will not let me to do. It will say that overlapping of the IP address is happening. So that's why we call it as routers are connecting network by network. So I have some network over here. Let's say I will have a different group of networks here. So basically there are a lot of networks, there are a lot of packets that will be forwarded. Okay, so how are these packet going to be read, or how are this? Let's say if this user number one is sending some packet, or he's downloading something from Google, so his packet must go in this direction, right, towards the Google server. Now let's say there is one more user who wants to download some Facebook videos. Now his traffic will go over on the same infrastructure, over on the switch, over on the core router, and then they will decide that Facebook is located somewhere here, right? So someone has to push the packet, and that's called as forwarding the packets. Okay, and who is doing the job of forwarding the packet? It's your router, and within the router you are going to configure all your destination path. Okay, so let's say if this is located on 10.10.10, now let's say these router has to know how to reach this destination. Okay, so how are two routers gonna communicate? They are gonna communicate over on routing protocol. And what type of routing protocols do we have? We have static routing protocol and we have dynamic routing protocol. Okay, so in the last class we have gone through static routing protocol. In the today's class, we will start up with one of the dynamic routing protocol, which is called EIGRP. Okay. So after few classes, we will go with the next dynamic routing protocol, which is called as OSPF. Okay. So what is an advantage of having EIGRP instead of static route? Okay. We have not discussed OSPF, so I'm not going to ask you anything about OSPF as of now. But what is a simple difference between static and EIGRP? Okay. So the difference is, in the case of static routing protocol, you need to manually add the lines, or you have to manually configure the routings. Whereas in the case of EIGRP, which is an example of dynamic routing protocol, there is an algorithm. Okay, whoever have discovered EIGRP, they have made use of some algorithm, and based out of this algorithm, EIGRP is going to find out the best way to reach to the next router or to the destination. Okay, so it only checks one basic thing about the path selection, and that is called as metric. Okay, metric is nothing but cost. So from EIGRP point of view, let's say it has to go via multiple routers. Okay, let's say the packet was meant from A to, let's say, R123. Now it can go via this direction or it can go via this direction. So what EIGRP is going to do is, so EIGRP is going to see a simple fundamental here, that is cost. If the cost is less, then it's going to prefer that route. Now you need to know how is EIGRP going to calculate cost. Okay. So before going ahead with some advanced, let's start with the basics of EIGRP, and then we will go step by step here. Okay. So as you can see on my display, you can see EIGRP stands for Enhanced Interior Gateway Routing Protocol. It's a Cisco proprietary. It was a Cisco proprietary, but in here to 2013, it's been called, it's been launched at open standard. Okay, nowadays EIGRP is no longer Cisco proprietary. It's a open standard. It's called as hybrid routing protocol. Also it's called as advanced distance vector. Okay, so one fine example of distance vector which we checked in the previous class was RIP, and the drawback of RIP is it's not going to check out the cost, it's going to just check out the number of hops. Okay, so what happens in is, let's say I have something like this. Okay, so let's say this was a serial link. So just to reach this destination, my router 1 is going to forward the packet in this direction. The only reason is it's going to take only first hop and second hop. But you had a very good path, but its RIP is not going to take that because number of hops are more, 1, 2, 3. So RIP is not going to take that. RIP is going to take this. But you know, the best path would be a Giga Ethernet. Okay, so Giga Ethernet was much preferable, not a serial link. So that's why we call EIGRP as advanced distance vector, because it's going to check out the distance, but it's more smarter. Okay, it's going to check the metric. It will check the metric of both the distance vector, and then it's going to decide which one to be considered and which one to be ignored. So as I told you about the algorithm, EIGRP follows dual algorithm. Okay, EIGRP is going to support V4, IPv4 and IPv6. EIGRP is also going to support variable length subnetting mask and classless inter-domain routing. Now, you might have seen we make unequal division of any subnet. Okay, so let's say this is an example of class C. Now I can make use of VLSM concept, and I can just split it in terms of /26. I can make it as 192.168 1 dot. Okay, sorry. Okay, let's say this is 100/28. Okay, let's say 192.168 1 dot 200/30. So if you see, this is whole a single network, 1.0 network. Okay, 1 dot, which is nothing but a class C example. But I am going to make use of the variable sublength mask. Okay, so that's VLSM. CIDR is nothing but this is a denotion for a CIDR value. Okay, if you just write /26/27/28, these are nothing but these are called as CIDR. If you just write the equivalent subnet mask like 255, 255, 255.128 or 224, now they become subnet mask. Okay, so usually they are the same thing, CIDR and subnet mask. It's about the way you write them. Okay, and this is how you make use of CIDR or VLSM to just break through a whole class C network into multiple network. But why do we do this? Because class C with /24 is going to give you 254 usable IPs. Now let's say I don't need 254 usable IPs. Okay, let's say I just need 10 IPs to some group. I need 20 IPs to another group. I need 30 IPs to another group, and I need like 5 IPs to some other group. Now, why should I waste 254 IPs giving to one group, right? So, in that case, everyone will have 254 IPs. Okay. So, I'm just wasting up 4 different network. So, what I'm going to do is instead of just a minute. Okay. So instead of giving 254 IPs individually, I can just break down the whole complete 254. Okay, I can just break down in such a way that every group will have its required numbers. Okay, so that's the point here. Instead of wasting the network, I would make use of a /24, which gives me 254 IPs, and I'll just break it. Okay, it sends partial or full update only when something is changed in network. Now this is a plus point of EIGRP. Okay, why do I say plus point is this is not going to send the complete database. Okay, so there will be no overhead on the routers. Whenever there is a topology change, it's going to send the EIGRP packet saying that so and so network is being deleted or so and so network has been added. Now that's called as periodic update. Okay, so it's going to send a periodic update, and then it's going to notify about any changes or any update in the network. As such, there is nothing that every 15 minutes there will be update packet sent in. Yeah, nothing like that. Only when there is a topology change, EIGRP is going to send. So that's improvising your resources inside your inside your routers. Okay, there is no extra overhead on over there. Now there is AD value. We discussed, if you remember, the 3 path selection factors in routing. The first one is called as longest match. The second one was called as AD, administrative distance, and third one was called as metric. Okay, what is AD? The trustfulness of any routing protocol. So every routing protocol will have its AD value, the trustful nature of that routing protocol. So in the case of EIGRP, it's 90 for internal, and for external it's 170. Okay, so you just need to remember this when someone asks you or give you some scenario. Okay, now let's say someone asks you like if he is drawing 2 or 3 different routers in on your path. Okay, now if someone tells that this is on EIGRP, this is on OSPF, and this is on RIP. Now who is going to be preferred? Okay, so basically your EIGRP gets preferred because of 90 AD value, whereas OSPF is 110 and RIP is 120. So always the lowest will win the election. Okay, lowest is going to get preferred. So in this case, it's your EIGRP who is taking the best path towards destination. Okay, so that's about the AD value. Regarding the hop count, so by default it said that EIGRP is going to support 100, but yes, you can just add them or you can tune it to 255. Okay, and one more advantage of using EIGRP is equal load balancing and unequal cost load balancing. So this is very important. Okay, OSPF doesn't support unequal, it only supports equal, whereas your EIGRP is going to support equal and unequal cost load balancing. So that is, let's say when I have multiple routers on my path and all of them are taking onto the same destination. Okay, 4.4.4.4. Let's say I am on 1.1.1.1. Now let's say I have two or three different path. Like in this case, I have first way, second way, and third way to reach the destination. Now let's say I want both the link to be participated for my traffic flow. Okay, so what I can do is I can bundle them. Okay, I don't have to bundle them. By default, this will be enabled. Okay, by default, on my routing table, I will see that EIGRP is considering both the route, that is first as well as the second route. That's called as equal load balancing. Okay, so that's in the case when this link and this link are same. That means if this is also giga and this is also giga, now that's going to be the same cost, right? So they are both the routes will be automatically put up in the routing table. It's called equal load balancing. Now let's say this was not giga, this was fast ethernet, and the last one was a serial link. Okay, I would need both of them to be part of my routing table, even though they are not equal. Okay, such scenarios are called as unequal. So in the case of EIGRP, yes, I can achieve that. I can set some percentage. Like I know what is the difference between giga and fast, right? Giga ethernet is 1 Mbps and fast ethernet is 100 Mbps. Okay, so I cannot give 50% and 50%. That would be not just justificable, right? So what I can do is I can make my traffic take the highest portion on the gig, that is, let's say, let's make it as 70%, and I would need 30% of traffic to be sent over on fast ethernet. So now this is achievable in the case of EIGRP, but in the case of OSPF I cannot do. Okay, so that's an additional feature of EIGRP. Now regarding load balancing, okay, as I told you, it's going to support equal load sharing or equal flow or the traffic. Okay, so how many links can you see in the routing table? So basically default is up to 4, but yes, you can configure up to 32. Okay, that's when you have a equal load, equal cost, and inside your routing table you see the multiple routes. Okay, so up to 4 is by default, but yes, you can go up to 32. Similar way regarding the timers. Okay, timers are very important. So let's say I have two routing or two routers which have EIGRP. Okay, now how is R1 and R2 going to keep some neighborship relation, or how are they going to uh, know each other, whether R1 is up or whether R2 is up, or whether R1 is down or R2 is down, right? So that's because of the periodic hello packets. Now this is called as periodic hello packets because it's having some constant timers. Okay, so in the case of a normal scenario, okay, a normal link, not very high link, it's always 5 seconds. So every 5 seconds you will see the hello packets are being sent on from the both side. R1 is going to send the hello packet towards R2, Similar way, R2 is also going to send the packet. Now, three consecutive hello packets will be sent. Okay. Let's say if the router 2 failed to respond back. So let's say in the first case, one packet was sent, router 2 sent the acknowledge packet. So in that case, they still say that yes, we have the neighborship. Now let's say router 1 sent first packet, no response. Router 1 once again sent the second packet, no response, and then it's sending the third packet, still no response. Now there will be no fourth packet. R2 will be considered as down. Okay, so that's the concept of hold timer. So by default in EIGRP, hello will be 5 seconds and 5 into 3. If you just multiply 3 times, that's going to be your hold timer. Okay. Now this is a standard in terms of EIGRP. It is into 3. So let's say you just change 5 from 5, you just change to 10. As per EIGRP mathematics, it should be into 3. Now that should be 30 hold timer as per the mathematics. But in case of EIGRP, let's say you just change the value from the default to custom. Okay, so don't think that the hello or the hold timer is going to automatically get configured. Okay, so what I'm trying to say is, in the case of OSPF, okay, and in the case of EIGRP, these timers are customizable. Okay, by default it is 5 and 15. 5 is hello, 15 is the dead. Okay, so what happens is, let's say I just want to change the value from 5, so let's make it 10 second as hello. So don't think automatically your hold timer will get shifted by 3 times, that's going to be 30 seconds. That doesn't happen in case of EIGRP. In the case of OSPF, it's 10 second and 40 second as dead timer. In case you just change from 10 to 20, automatically your OSPF is going to change it. Okay, so now it becomes into 4, which is nothing but 80 second. Okay, that's in the case of OSPF. Automatically the hold timer or the dead timer will be shifted into 4. But in EIGRP, you just have to do on the both side. You just have to manually do on the both side. Okay, but yes, they are customizable, and this is a default in the case of Ethernet. In the case of Ethernet interface, these are default. Similar way, you have some high links, high circuits, where the default value will be little different, which I'll tell you in few minutes. Okay. And regarding EIGRP, yes, they are a multicast protocol. Okay, and this is the multicast IP. So initially, when I'm bringing up both the routers on EIGRP configuration, so as we know, the hello packets will be sent. Okay, now this hello packet will be sent over on this multicast IP. Okay, that's the destination IP which is inserted in the hello packet. It will be 224.0.0.10. Now this will be enabled on this, or this will be listening. Okay, that this IP is listening inside this router. So that's why when the hello packet just enters or hits on the R2 where EIGRP is already configured, it will have this IP listening. Okay, similar thing happen also on R1. As soon as you enable R1 with EIGRP protocol, it's listening on 2240.0.100. As soon as some packet comes with a destination of destination mentioned on this IP, this multicast IP, that's your router when it's going to understand, well, this is a EIGRP packet and let me process this. Okay. Now what happens if you don't have this IP enabled? Your packets are going to get dropped, as simple as that. So looks like I was disconnected. I hope I have not uh, covered anything much in that small fractional second. So am I audible now? Do you guys see my screen? Am I audible? Okay, great. Okay, okay. So regarding the multicast, in the case of multicast, as I have told you already, multicast send the packets to group of uh, devices or group of uh, boxes which are listening on that multicast IP. So let's say this is enabled on EIGRP, okay, and out of this, few are on EIGRP, few are on OSPF, okay. So now what happens is when you're sending some hello packet, the hello packet will have two components. One is source and the other one is destination. So in the destination is where you're going to enter this IP address as 224.0.0.10. And now when this hello packet is sent over on these EIGRP routers, that's going to listen. That's those EIGRP runs over on this multicast. Why is other router going to discard? Because the multicast IP of OSPF is different. It's this. Okay. So because of change in the multicast address, now whatever packets which is originating for EIGRP is going to get discarded by OSPF routers. Okay. So multicast is something which communicate only between group of similar protocol. They are not going to communicate with anything else like OSPF in this case. Okay. So that's the backend flow of EIGRP. This is the IP which is listening on the destination side. And yes, EIGRP is going to support MD5, okay, and by default auto summarization is enabled. So what is this about authentication? So by default these EIGRP packets are going to be plain text, okay. So in order to encrypt, I can make use of MD5 and auto summarizable. Now that's something important. So what is auto summarizable? So let's say I have 192.168.1.0/24. I have 192.168.2.0/24. I have 192.168.3.0, 24, 4.0/24, 5.0/24. Now there are couple of networks which is a part of class C, okay, on /24. Now what happens is the more number of individual networks I have, okay, the more number of your update packets, your query packets will be transmitted between the two routers. So what I can do here is I can summarize them into 192.168.0/0 and I can put it as 16. Now all these networks are part of this broad group, okay, and this group will be advertised over on between R1 and R2. Now that's called as auto summarizable, which is enabled, okay. So we will see this during the lab as well. So as of now, just remember, you are just making use of a broad network instead of sending individual. Now yes, this can bring you drawbacks, okay, because from the troubleshooting point of view you will not come to know or you're not aware of that exact network which has an issue here, okay, because you will only see this broad network and behind this broad network there will be plenty of smaller network. Now how will you troubleshoot? How will you know that the server belonging to 1.0 are having some issue, right? So troubleshooting becomes little problematic. But from the point of overhead on the devices, since you are not processing individual networks over between R1 and R2, so that's something which is going to help you by reducing the overhead on the devices. Okay, so very short summarization of EIGRP. So as we go, you will see lot many things, some advanced things also. Okay, so those were some basic things. Now let's see about the advantage of EIGRP. EIGRP when compared with OSPF. So I would mention that way. Okay, OSPF or RIP, but as you know, RIP is outdated. No one is going to use it. Okay, so it's always EIGRP versus OSPF. Okay, well, so EIGRP is considered to be low usage of network resources during normal operation. Only hello packets are transmitted. Okay, so that was my point even earlier. It's not going to carry your topology change, or it's not going to carry all the link state advertisement. Okay, it's just going to maintain hello packets between the routers. Something is changed, then there is a new packet coming in which is called as update. Otherwise, it's just a hello packet between the two routers. It's going to be consuming very low usage of the network resources. Okay, when a change occurs, the routing tables are propagated, not the entire routing table. Now that's again a good thing. So let's say this router R1 is aware of 5 networks, and R2 is aware of, let's say, 4 networks or 10 networks. Okay, now let's say one of the network is going down. Okay, you don't have to carry the complete other routing tables to R2. Okay, you can just tell that this is down, this is down, so you just remove it, and then R2 will remove that. Okay, so that's what it says. When a change occurs, only the routing table changes. Whatever changes happen will be propagated, not the entire routing table. Okay, so that's again an advantage in case of EIGRP. In OSPF, what would happen was, you bring any changes, it will be sent to the DR, and then DR is going to send the routing tables information to all other routers. Okay, the complete routing table will be sent. So at the end, all the routers along with this router are going to have a consistent network. So let's say this is aware of 10 networks, so this also is going to be aware of 10. This is also going, any change happen here, every one is getting notified. But in case of EIGRP, that is not the way. Okay, the number of networks can be different. Let's say on this I have 10 networks that's been read by EIGRP router. Now that can be different. Let's say this only knows about 2, this only knows about 4, this only knows about 6. So whatever is required, it's going to take it, not the complete routing table. Regarding the rapid convergence, okay, so in the case of rapid convergence, okay, EIGRP is also called as, or also meant as, a faster convergence. In the case of primary link goes down, the secondary comes up. The reason is, let's say I have something like this. Okay, let's say I have some topology in this scenario, this case. So by default, this is the path. Okay, it's called as primary path. Now what happens is, in the case of EIGRP, EIGRP is going to keep a backup path as well, and that's called as feasible successor. Okay, I'm just writing a short form here. It's called as feasible successor. Now this feasible successor will not be inside routing table. Okay, so only your best route will be put up in the routing table. If that is going down, your backup, which is also called as feasible successor, will be put up into routing table. Okay, that's why it's called as a faster convergence uh, protocol. Okay, in case of RIP, that is not the way. Okay, in the case of RIP, it would have done the recalculation. It would have easily lost up to 120 seconds, 90 to 120 second, to recalculate, to see what are the path hops to reach destination, and then it would have put in the routing table. Okay, in the case of in the and one more thing about RIP is it's only going to maintain one routing table, that's called as a normal routing table. Okay, whereas in the case of EIGRP, it's going to maintain different kind of tables. So let's say I have routing table, I will also have something called as topology table, and now this backup link will be part of topology link. Okay, so your primary will be still part of routing table. If that goes down, you have something backup inside topology table, and it will be immediately put in the routing table. In the case of RIP, it will not have these kind of two tables, it's only having routing table. Okay, so that's why EIGRP is also faster in nature. Okay, and yes, it's a enhanced distance vector. It's all relying on this algorithm, okay, to find the shortest path. So always remember, it's the metric that's important for any protocol. Okay, terms of metric, we find the shortest path to reach the destination. Okay, regarding some changes of EIGRP. Well, there were two different EIGRP versions, version 0 and version 1. After, let's say the Cisco iOS version earlier, 10.3, 11.0 and 11.1, there were these two versions of EIGRP. But as of now, we only have one version. Okay, so as of now, you will not see any platform where you will see version 0 or version 1. But yes, when we had these iOS softwares, we had two different versions of EIGRP, and yes, there were difference in terms of timers and in place of the concepts as well. Okay, as of now, don't worry, it's just one EIGRP, but that's a little background information on EIGRP. Okay, now let's take this as an example. So let's say router 1, okay, let's say I have router 2. So from point of router 2, I just need to see the best way to reach network A. Okay, so it can go via this direction, or it can go via this direction. Okay, so both the possibilities are possible, right? Both possibilities can happen in this scenario. So from router 2 point of view, to reach network A, it can go via this direction, or it can go via in this direction. Now let's say in case of RIP, it would have taken up this path. Okay, that is your router 2 sending to router 1, and then router sending to the destination, which is network A. Okay, the reason is RIP learns basis on the hop counts. Okay, but interesting thing here is, this is not a giga link. Okay, this is a serial link. Serial link, which is 64 kbps bandwidth. Rest, let's say they are all giga Ethernet. So do you still think the RIP decision is a wiser decision of going across in this? That's no. Okay, because if you check it from the point of the cost or metric, you will realize that this is taking the lowest cost. Okay, let's say if this is taking 100 cost value, this 2 hops is taking 1000 of cost value. Okay, and that's where your EIGRP is acting smarter, because EIGRP is not just checking the hop counts, it's checking multiple factors associated with this interface. Now what are those factors? Factors like bandwidth. Okay, what is bandwidth? Bandwidth is nothing but the maximum packet that this link can transmit at a time. Okay, so it in case of giga, it is 1 gigabits per second that a bandwidth of this link is, whereas in case of serial it's just a 64 kbps. So what are EIGRP going to consider? It's going to consider bandwidth, it's going to consider delay, okay, and multiple other factors of these links that the packet are traveling. So based on these decision, it's going to make it's going to calculate the metric, and that's how you will know which is a better path in case of EIGRP. Okay, so that's what something we will see in coming few slides. Okay, so as I have mentioned here, if R2 has to reach to network A, so R2 R1 network A. Okay, so basically this R2 R1 R network, okay, it's a better path. And when you have R2 R3 R4 and then network, okay, in case of RIP this would have been dropped, but in case of EIGRP this would have been the best path because of the metric calculation. Okay, so that's something which is written over here. Okay, now quick EIGRP facts. As I told you, the hello packets and the dead interval are customizable. This is a command to customize that. Okay, hold timer is nothing but for the amount the neighborship relation will be still active. Okay, and once it misses consecutive 3 packets, 3 hello packets, it's going to remove that neighbor. So that's called as hold timer. Okay, so by default it's 15 second. So there are two types of links. Okay, so one is called as 5-second hello and one is called 60-second hello. This is in the case of Ethernet medium, whereas this in the case of a heavy bandwidth or heavy circuits like your T1, T2 circuits. So in such circuits, you don't want a very often hello packets. Okay, so you would prefer keeping 160 as your hello, and if you just do into 3, that would be the hold timer in such heavy bandwidth circuits. Okay, but in case of Ethernet, fast Ethernet, giga Ethernet, it's default 5 and 15. Okay. Okay, and yes, there are some criteria that don't have to match in EIGRP. Okay, in case of EIGRP, the two routers don't have to have the same hello and hold timer. Okay, to form the neighborship. Whereas why I'm considering this is, in case of OSPF, the hello and dead timer must be same to form the neighborship between two routers. But in the case of EIGRP, they don't need to be same. Okay, you can have hello 5 and 15 here, and you can have 10 and let's say 30 over here. Still they will form the neighborship in the case of EIGRP. But in the case of OSPF, no, they will not. Okay, hold timer is included in the hello packet, so they should stay alive even though the hello interval and do not match. Okay, this is just a small explanation why they don't have to match. Okay, while there is no direct way of determining what the hello interval is on the router, you can infer it from the output. So it's just the command where you can see the timers. Okay, so if you make use of show IP EIGRP neighbor statement, you can see what is the default timers configured inside your router. Okay, so there is no other way to see the timer. So this is the command which will show you the timers. Okay, show IP EIGRP neighbors. Okay, now this is the table that you get when you trigger out this CLI command, show IP EIGRP neighbor. Okay, these are the two neighbors over here. Okay, fine. So regarding EIGRP neighborship, okay, how are the neighborship established? So let's say I have R1 router and I have R2 router. Let's say I have enabled EIGRP. Just few seconds ago, I enabled EIGRP. Now both are listening on this multicast address. Okay. So what is going to happen is, as soon as EIGRP gets enabled, by default at the background this IP is listening on both of them. So a hello packet will be initiated from router 1. So once hello packet is initiated, now this packet is multicast in nature. Okay, it's multicast in nature and it is destined for this multicast address on the other side. As soon as router 2 receive some hello packet from any router, even though they are not neighbored at this moment, if router 2 receives some hello packet, especially the hello packet from EIGRP, what R2 is going to send is, R2 is going to send a unicast packet. Okay, unicast is 1 to 1. And what is the content of this unicast going to be? It's going to be the complete routing information. Whatever routing table of R2 is, it's going to send a quick unicast message to R1. Okay, and that kind of packet is called as update packet. So if you see, first packet was hello packet. Router 2 made use of update packet to send the complete routing table. Router 1 said, I'm acknowledging you back. Okay, and now that's again a unicast packet. Okay, so that's your third step, going back to router 2. And now what happens is, R2 is now going to initiate a hello packet. Okay, now that's a multicast packet. And now R1, it's going to share its all routing table and it's going to acknowledge, and then these two are called as neighbors. Okay, R1 and R2 are going to be called as neighbors. So these are few steps in case of EIGRP. Similar way, when I take OSPF, you will see some other kind of steps. Okay, the 7 states we normally call, where you will see the each thing. Okay, but in the case of EIGRP, this is the way the two routers form neighborship. So totally 6 steps. You should always remember there was no broadcast packet used. Okay, from point of interview, there was no broadcast packet. This was a multicast, unicast, unicast, multicast, unicast, and again unicast. Okay, so that's how the two neighbors are formed. Now let's see how the two routers form the neighborship, they exchange the topology, and how the best route is getting placed in the routing table. Okay, so they are divided into 3 EIGRP state. The first one is called as neighbor discovery. So that's nothing but whatever we just discussed just now, but we'll see if we do have any extra points to be added over there. Okay, so the first step here is neighbor discovery, and as we know, the packet were sent in multicast and unicast, they form neighborship. But let's see from the point of timers and all other things. Okay, so EIGRP will use non-periodical incremental routing updates. Okay, there will be no periodical, there's no incremental happening basis on 15 minutes or 30 minutes. It's only when your network topology has changed, that's when the incremental update will happen. Okay, EIGRP will only send routing update about the path that have changed when those paths change. That's what we discussed. They're not going to send the full routing table. Okay, it's just going to send that faulty or that newly added up route, which is a latest information, not the complete routing table. In case of OSPF, it will send the complete routing table every time. Okay. Okay, the basic problem with sending only routing update is when you may not know when a path through a neighboring router is no longer available. Okay, that's when, let's say I have multiple routers. Okay, let's say they are going to this destination, which is 4.4.4. Let's say by default my EIGRP has considered this path to send the routing table. Okay. So in the case of EIGRP, let's say this goes down for some reason. How is this EIGRP going to know that there is one router in transit which is stopped working or which is not working now? Okay, because whatever happens is not going to share to this person. It's just between the two neighbors, or might be to this neighbor. Okay, so whatever topology change, that's not visible to this person, because that's how EIGRP works. Okay, EIGRP is going to only notify the neighbors, not to the throughout the topology. Okay, so that's one of the drawback in the case of EIGRP. Whereas in OSPF, what would happen was, even though the topology was dropped here, every router would have got notified saying so and so network has gone down. Now what to do? Now the second best path would have been put up in the routing table. Okay, which don't happen in EIGRP. That's what it said, that there is a drawback here. Okay, so expecting a new routing table from your neighbor, EIGRP relies on neighbor relationship. Okay, so from the point of R1, it's just sending the packets. Now it's up to these router to decide whether to send or not. Okay, so in this case, it's not going to send, and as soon as the neighborship goes down, now EIGRP will be notified that that's gone down, and now EIGRP will make use of the feasible successor, which is nothing but the backup link that was this in this scenario. Okay, and now this gets triggered, or this get put up inside the routing table, and now all the packets will take up this path. Okay, so that's a drawback here in case of EIGRP. But if you see from the positive side, there is no periodic update. The whole routing table will not be advertised. Okay, it's just the incremental and part by part information. Okay, so let's assume the neighbors are formed at this step. So let's say that was step number 1. Now what is step number 2 is, these EIGRP routers will maintain a separate table called as topology table. Okay, so let's say the first table was about neighbor table. Okay, so the first table was neighbor table, where it's going to put up all the neighbors. So let's say this router has a neighbor relationship with R2. Now this information will be put up in this table. Similar way, this router has a neighborship relation with R3. Now that will be part of this. Okay. Now apart from neighbor table, there is something called topology table, and after topology table there is something called as routing table as well. So the routing table will contain only the best path. Now then, what is topology table going to consist of? It's going to consist of all your backup path. Okay, so in case of best path goes down, your backup can come over and start its work. Okay, so let's see what is topology table. Unlike RIP and EIGRP, do not rely on routing table. So as I told previously, in case of RIP and IGRP, they only have routing table. Okay, they don't have topology table. They are just going to have routing table. But in the case of EIGRP, it's going to maintain a separate topology table. Okay, and topology table for all other information that is required to operate. Instead, build a second table, a topology table, which will install routes in the routing table. Okay, and this is the command that we can check all the routes that's within the routing within the topology table. Okay, so the topology table contain the information needed to build the network reachability. Okay, so let's say I have routing table, I have neighbor table, I also have topology table. So whatever links you have, they are actually gone through all the required parameters. Okay, that is lowest bandwidth, total delay, path reliability, path loading, minimum path, maximum transmission unit, feasible distance, reported source. So it has gone through all this, and then the topology tables are formed. Okay, it's not that it's going to keep all the information. In case of OSPF, which is a link state advertisement. In the case of OSPF, inside topology table, you can see every routes or every possible routes. Okay, not just a backup, even any kind of routes. But in the case of EIGRP, the best or the second best route will be put up in the topology table, but it has already gone via all these parameters, and after that whatever is best will be put up in the topology table. Okay, and these are the few parameters that I was telling in the case of EIGRP. Okay, so let me tell you where exactly these are getting checked up. Okay, it's always on the exit interface. Okay, so let's say I am going from 1.1 towards 4.4.4. Now when I go in this direction, it's my exit link. Okay, now let's say this packet, uh, for this packet, this is the ingress. Okay, so ingress is not going to manipulate any kind of EIGRP calculation. It's the exit that's going to modify. Okay, so ingress is just transparent for any protocol, not just EIGRP, even your OSPF, the same fundamental. So when you talk about any protocol, if someone asks you which is the interface that manipulates the traffic, whether it's your ingress, okay, let me write here, ingress is nothing but incoming traffic, or it's your egress traffic. Egress is nothing but outgoing traffic. So for the protocol, it's always egress traffic that's manipulating the changes. Okay, so let's say this traffic hits here. Now this interface is not going to modify anything or manipulate anything. Okay, it's this interface that's going to manipulate. So based on this all manipulation, these are the parameter that is checked. Okay, the bandwidth, the delay of the interface, the reliability, the loading, the MTU set on this exit path. Okay, this MTU is of no point of consideration. It's this exit MTU. Okay, feasible distance, reported distance, route distance. Okay, so it's of all the exiting interface that's matters in the case of EIGRP calculation. So once they calculate, they will be put up in the topology table. Okay, and from the topology table, the best one will be placed in the routing table. So that's how EIGRP make use of its various table to find out the best path or the best path to reach the destination. Okay, now regarding the EIGRP metric, how is you going to find out the best path? Okay, so as we know, as I was showing you some diagrams, so let's say I have this topology and I want to reach this destination, which is 4.4.4. okay, and I have 1.1.1. now just assume that uh, someone asked me to explain the flow of the packet flow in case of EIGRP. Okay, so in this case we need to explain the packet flow from one point to second and third and fourth. Okay, so always remember it's about the matrix. Metric is nothing but the cost. Okay, the shortest cost will win the election. It can be via this or it can be via this direction. Okay, so let's say if they have a serial link in between. Now the bandwidth is different here. If the bandwidth is different, uh, the cost will also get changed. Okay, now let's say they are making use of the same link, same bandwidth link, that is all everywhere the GI links. Okay, so in this case the default load balancing will happen and both of them will be preferred. Okay, so that's a behavior of EIGRP. So let's say from this diagram point of view, okay, I have this topology. So let's say my router 1 is sending some packets to network A. If you see from the given value, they are nothing but bandwidth and delay. Okay, So it says the bandwidth of this link is 56 and the bandwidth of this is 128. Okay, and then we have the same link. So the bandwidth and delay is over here, and we have the bandwidth and delay over here. So I will just show you, I'll just show you how is the calculation happens, or how is the calculation getting over here, and which path is getting elected. Okay, so first let me tell you what is the formula for calculating metrics. So this is a formula to calculate EIGRP metric. Okay, but don't worry, this will be simplified. Okay, the reason why we simplify this is, in the case of EIGRP, I just don't have to worry about everything. Okay, I just don't have to worry about the bandwidth, load, delay or reliability. Okay, so in case of bandwidth and in case of delay are the only two factors which have to be considered for my metric calculation. Okay, rest of the things like load, reliability, I can just ignore them. Okay, so I can just ignore load and reliability. So what are the factors by default? What are the factors by default? It's bandwidth, load, delay, reliability. Okay, which are the main factors for your EIGRP cost calculation, but we can ignore load and reliability. Okay, we can ignore them and we can just keep consideration of bandwidth and delay. Now when I keep only bandwidth and delay, and if I just put others as 0, so my formula gets simplified to this. Okay, now they are only bandwidth and delay, so my cost, okay, overall is a sum of bandwidth and delay. Okay, so in order to manipulate the behavior, we are making use of some k values. Okay, these are some constant values. In case of EIGRP, k are called as constant values. Now these k values can be modified. Okay, they can be modified in order to change the behavior of metric calculation. Okay, you can see there are a lot of values. As I told, we are going to ignore few of things. Okay, so let's say I just ignored k2 value. So if I ignore k2 here, this is going to be 0. Okay, what is k3? That's fine. I have k4. K4 is 0. Where is k4? This is 0. Okay, so the whole thing is going to be 0. And also I have k5. Where is k5? Or this is k5. Okay, so that's how you just are going to have only k1 into bandwidth. Okay, and what else do we have here? So we have (256) minus load, okay, plus k3 into delay, okay, into 256. Now this is the simplified formula for EIGRP. Now if I just check you, if I just cross verify, let's check that. So you can see this metric equals to bandwidth plus delay. Now that's this way, k1 into bandwidth plus k3 into delay. Now yes, we can change this k1 value. That is why this k is with us. Okay, we can just tune this k values. Okay, now regarding the calculations of EIGRP, let me quickly explain you the few things here. Okay, in case of bandwidth calculation and in case of delay calculation, because we know metric is directly based on bandwidth and delay. So how do I calculate bandwidth? The bandwidth, let's say, in the case of first example, in the case of 56 bandwidth, how am I going to calculate that? I'm going to calculate 56 with the help of this formula. Okay, and in the second line I have the delay formula. Delay is nothing but okay. Now again, one important thing that you should know, when I say we have the two important parameters, so bandwidth is going to be the shortest bandwidth or the lowest bandwidth of this topology. Okay, so let's say this is one path. So throughout the path, which is the shortest bandwidth? So let's assume this is a 56, which is shortest. Okay, so over here it's more than 56 and over here it's more than 56. So I'm going to only compare 56 because that's the shortest bandwidth. In the case of delay, that's going to get added up. Okay, so that's nothing but this value will be added up with this delay, and then that will get added up with the last delay. Okay, that's nothing but with the packets are going from A to destination. So in the case of delay, it's the complete sum. Okay, sum of the total path. In the case of bandwidth, it's just one bandwidth, the lowest bandwidth that's getting triggered. Okay, in the case of delay, it will be 1000 plus 100 plus 100. Okay, that's why you will see here the calculation also shows you something accordingly. So for bandwidth, we just considered 56. In case of delay, I am going to consider the whole sum. Okay, this you should know in case of solving any EIGRP related questions. Delay is something which is throughout. It's a sum between all the different hops. Whereas bandwidth is any shortest bandwidth only. Okay, and this is the whole calculation. Okay, as we know, it's bandwidth plus delay into 256. Okay, and I get this as the cost. So this is the cost for the first path, if I'm not wrong. Okay, so that's nothing but this cost. So this cost is something 46 some value. Okay, similar way I also have to find what is the cost value for this. Okay, the same formula once again, nothing changed. So let's see what is the value for the second path. So bandwidth is better here, 128K. Total delay is the total topology delay, and if you just make use of the formula, you're going to get this value. Okay, so from this diagram, from this diagram, if you just see the cost value, it is 40 and some value, and this is in terms of 201 and so on. Okay, which is lowest now? As you know, metric is cost. Who will win the election? The lowest one will win the election. So in this case, this is the lowest path, and this is going to win the election. Okay, so this is how EIGRP will select the path. In case of path selection, this is how EIGRP will see which is the best path, and it's going to forward the packet to that path only. Okay, what about the second path? Do you think this path will be ignored completely? Do you think this will be just ignored and will not be used? No. In case of EIGRP, as I told, this will be called as feasible successor. If for some reason this goes down, we have this inside our topology table. Okay, inside our topology table, this route will be acting as feasible successor, which is a backup link, and it will immediately be put up in the routing table as soon as the main links goes down. Okay, great. Now regarding the EIGRP tables, as we discussed, we have three tables: neighbors table, topology table, routing table. And what are the command to check this? It's show IP EIGRP neighbor, show IP EIGRP topology, and show IP route. Okay, 3 commands for just showing or just seeing each table detail. Okay, so what is neighbor table going to be consisting of? Any neighborship relation. Okay, let's say R1, R2, R3. So the neighbor relationship between these will be stored up in the neighborship table. Okay, so this table will be on the 3 router individually. Okay, what is topology table? So let's say there is some path, okay, routing path, or let's say there is a backup path. So that's something which will be stored in the separate topology table. What is the routing table? It's your best path which will be put up in the routing table. Okay, the table goes same for OSPF also. In case of OSPF also, you have the similar table, okay, neighbor topology or routing table. So in OSPF we also call this as database table. Okay, in case of EIGRP, it's 3 of them: neighbor table, topology table, and routing table. Okay, so this is regards to the table explanation, which I will show you once I configure the lab. Okay, so I just don't want to take that. This is just when you are revising or checking out the notes during interview or preparing for exam. Okay, so just keep this on hold as of now. I'll tell you what is what. Okay, EIGRP metric. EIGRP uses metric to select the best route from all available routes to destination. Okay, these are the 5 components. As per theoretical, these are the component, but as per practical, we are going to ignore reliability, load, and mtube by just taking it as a default value. Okay, ignoring in the sense we just assume these are by default throughout its default the same throughout the topology. Okay, so we just consider bandwidth and the delay. Delay is nothing but the delay from one router 1 to router 2, the delay for the packet to switch from one router to second router, the time it takes. Okay, okay, this is the path calculation, which is uh, this is a standard reference 10 to the power 7, and this is my bandwidth, minimum bandwidth. Okay, as you know, it's one minimum bandwidth throughout the topology, whereas in the case of delay, it's a sum of outgoing interface. Okay, don't consider ingress, it's a outgoing interface. Again, some quick examples to see those values. Okay, so this is your metric bandwidth, this is your delay. You will have the formulae over here which I have shown you, so that you can just go towards the mathematics here. Okay, so how you got this metric 156160? Okay, so what I'm trying to show here is how did you get this value is by this calculation. Okay, so you need to know bandwidth, you need to know the delay. So if you see the two bandwidth, which bandwidth are you going to consider? The lowest one is going to be considered. That's why you are only going to consider the lowest bandwidth. From the point of delay, you are going to add both of them. That's why you're going to add them. Okay, and then this is the formula to get metric, and you get 156160. And in the routing table, in the routing table, you will see from R1 point of view, if any packet has to reach to 2.2.2, so it will go over EIGRP. Okay, D denotes EIGRP, 90 denotes the AD value, this denotes the metric. Okay, via this interface 12.2, which is nothing but this interface. So your routing protocol is going over on this interface to reach this destination, and these are the values that's been stored. Okay, Okay, these are something like path selection, all those things which we can do in the next class. Okay, I'll talk about the packet types. So how many packet types do we see in the case of EIGRP? As soon as I bring EIGRP up, they are going to send the hello packets. Okay, so we have hello packets used to identify neighbors. They are sent periodic. So by default, it's 5 and 15. Okay, 5 seconds for hello, 15 seconds for hold timer. Apart from that, we also will see the update packet. Okay, in the case of update, it's to advertise the route, only sent as multicast when something is changed. We have acknowledgement. For any update, there will be acknowledged back, so that's just a receipt kind of packet. Okay, and then we have a query packet, and we also have a reply packet. Query is when let's say to find the alternative path. Okay, so let's say you have this connectivity. Okay, so this was the primary path and this goes down. Now you are sending some query packet to make sure if this path is up or not. Okay, or to find which is the alternative path, because since this is down, you need to find the alternative path. Now to make use of that, you are going to make use of query packet. Reply is when you have some response back. Let's say if you know there is an alternative path, you are going to respond back saying that yes, I have a immediate or I have a alternative path to reach destination. Okay, how do you see all this packet? With the help of this command, show IP EIGRP traffic, which will show you how many hello packets have you sent, how many update, queries, replies and acknowledgement. Okay, so each function will have its own packets to carry on the job. Okay, so these are all about hello, update, query, reply and acknowledge. Okay, okay, we also have some terminology which I will take in the next class. Okay, so that those are important thing. We have EIGRP summarization. We have two types of summarization: auto summarization and manual summarization. And you just know what exactly is this. Okay, we will do this lab and I'll take this in next class, just summarizing it. So let's say I have couple of network like 1.0, 2.0, 3.0, 4.0. I'll just summarize them. Okay, 192.168 0.0 slash 16. Okay, I'm not going to send individual networks. So it has its own plus and minus. It's of course going to reduce the head counts on the CPUs, but troubleshooting is little problematic. You will not know who is the actual culprit. And then we have EIGRP load balancing, which are two. In case of EIGRP, equal by default it's equal, but yes, we can also have unequal configured. Okay, and then the basic configuration. So these are few things in EIGRP. Now let me quickly show you the basic configuration of EIGRP in today's class, and the rest will be taken up in the next class. I don't want everything in one class and then at the end we just don't know, or what we just we then realize that we were a little faster or something like that. Okay, so let's say this is a topology where I would like to test my EIGRP functions. Okay, so what I am going to do is I am going to consider this as source and this as destination. Okay, so I'll just show you few simple things as of now, that is how to configure EIGRP, how to see the contents of a neighbor table, topology table and routing table, and then yes, we can see if something is pending. Okay, so these will be covered in today's class. In the next class we will try to path manipulate, we will see the equal load sharing, and we will see the unequal load sharing. This will be taken up in the next class. These are some advanced topic. Okay. So as of now, let's build some simple EIGRP. Let me show you what is the content of EIGRP. Okay, so I have the first router. So let's see what do I have here. Okay. Show IP int brief exclude unassigned. So I have 4 interface. Okay. The 3 physical interface and 1 loopback interface. Now where is all these from my diagram? So over on E0/1 I have 10 network. Okay. Over on 0/2, that is this, I have the 40 network. E0/3 I have 20 network, and I have a loopback for my testing the packets. Okay. Similar way, I'll just make sure my basic interface configurations are present or not. Show IP int brief exclude unassigned. So I have the 2 interface for Tokyo 10 router, which is this router. So one over here, one network over here, 10 dot, and on the other network I have the 30 prefix. Okay. Similar way on Tokyo 29. Now where is Tokyo 29? That is this. So it must have 2 physical interface. Show IP int brief exclude unassigned. Okay. So one in network 50 series network on 0/1, and I have 0/2 as 40 network. Similar way on Tokyo 12, let's see show IP int brief exclude unassigned. So I have 50 dot network and I have 20 dot network, but there is some problem here. The problem is it is not 50, it's a 60. Okay, so I'll just quickly change that. So let's go to interface 0/2. Let's say its IP address 60 255 255 shut no shut. Okay, now let's check the IP. Okay, so I have 60 and 20. Okay, 20 on this side and 60 on this side. That's also fine. Now let's see from the last router point of view, that is Tokyo 30. Show IP int brief exclude unassigned. So I have 50.0, that's here. I have 60.1, which is over here, 30.1 over here, and then I have the destination 4.4.1, which is configured as a loopback. Okay, just all basic reachability. You can ping point to point just to make sure they are reachable. Okay, they must be reachable to form your EIGRP neighborship. Now since I'm telling this point, so there are few times your EIGRP neighbors will not come up. Okay, reason could be your interface was down, your neighbor interface was down. Now due to that, then EIGRP neighborship will not come up. Let's say there was some ACL access list put up here. Okay, if there was an access list which is restricting the flow of EIGRP packets, that can also hamper your neighborship. So that's why I say, when you bring up your EIGRP, you must see that these two, the directly connected must be reachable. Okay, that goes good for all the routers, all the interface. They must be reachable on ping. Okay, once we have the basic reachability, we can enable EIGRP, and configuring EIGRP is very simple. Go with router EIGRP and go with some autonomous system. Now, this could be the third criteria to say neighborship wouldn't come up. Okay, so let's say the autonomous system is not same. Okay, let's say you have a autonomous system of 100 over here, but you are going to keep autonomous system of 200 on other routers. Now this will not form neighborship. Okay, so those are the three criteria. First criteria, if interface was down. Second criteria, um, if there was access list over the path. And the third criteria, if autonomous system is not matching. So these three are some basic troubleshooting in case of EIGRP neighborship not coming up. Okay, so in this case, let's go with autonomous system 100. As we know, to advertise any command, as we know, to advertise any network, I can make use of network command and I can just advertise these network, that is 192. One second. So I can make use of network command 192.168.10.0 and whatever wildcard mask. I can make use of network 192.168.20.0 and the wildcard mask. Okay, or just for a simplicity, I can go with this statement. Now this statement is allowing all the networks. Okay, so since I'm just going with some basic configuration, I'll only put up 0.0.0 as of now. That's nothing but I'm advertising the whole networks. Okay, press enter. Similar way, you go on to all other routers, go to router EIGRP 100 network 0.0.0, come out of this. Router EIGRP 100 network 0.0.0 and router EIGRP 100 network 0.0.0 conft router EIGRP 100 network 0.0.0.0. Okay, so what happens is we can see the neighborship coming up. Okay, so how do we see the three tables of EIGRP? It's show IP EIGRP neighbors, and we have show IP EIGRP topology, and we have show IP EIGRP, or we can go with show IP route EIGRP. Okay, so these are the three tables that we discussed in today's class. Okay, now if someone asks you to expand on these individual tables, like what are these? Okay, what is this component inside neighborship table, or what is within the topology table, or what is within the EIGRP routing table? So you should know to some extent. Okay, I don't say 100%, but it's good that you know a lot of the components here. Okay, so let me just brief you. Okay, so let me just show you what are what. So H represent handle. So that's nothing but on which level the routing neighborship were formed. Okay, so this was formed first, then this, then this. So the three neighbors, and they are getting a that's just show the list of neighbors in a order the route was learned. Okay, that's regarding the first component. This is nothing but the neighborship. Okay, so if I just show you from my topology, so I am as of now on this. So it is forming neighborship with this, and with this. So that's why we have three neighbors. 0, 1, 2, 3, and you will see the IP address 10.2, 40.1, and 20.2. Okay, so if you want, I will place them next to next, something like this. So we have topology as well as output kept next to next. Okay, so we have three routes: 10.2, 20.2, and 40.2. Well, so this is nothing but the IP address of the neighbors. These are the interface from where this EIGRP was learned. Okay, just a just a minute. Give me a second. Hey, hi. Sorry, I'm just starting. Okay, so as I was telling, these are the interface where EIGRP was learned. Okay, so in this case, it's 0/1, 0/2, and 0/3. So you can see the three interface for Tokyo 7, Tokyo R7. And the next component, it's about the hold timer in seconds. Okay, as we know, the timers are 5 and 15 by default. And what does it significant? It says that if this timer goes below the threshold, so let's say if the first hello was sent, second hello was sent at 10th second, and then you have the 15th, that was the third packet. Okay, third hello, and now there was no reply. Your neighborship will be taken down. Okay, so this neighborship will be taken down. So that's this whole timer is. Okay, it's in a so if I just redo, you can see this is going in a descending order from 15, 14, 13, 12 till 1. Okay, and you see the uptime. So basically, for last 1 hour 44 minutes, these neighborship are up. Okay, so you can see the neighborship time for all the three. Now, what is SRTT? Okay, SRTT is nothing but smooth round trip time. Smooth round trip time. Okay, and it's in a millisecond. So what is it doing is, so let's say the hello packet was sent, and this router, the router 2, sent a acknowledge packet, right? So what is acknowledge? It's just a receipt. So let's say if there was a packet sent to the neighbor, and the neighbor is sending an acknowledge. Now that's a complete circle. Okay, smooth round trip. So that's this timer. Okay, so it says it sent, it took 9 milliseconds for this smooth round trip between R1 and R10, or R1 and R29, R1 and R12 accordingly. Okay, so you can see for every neighbor there is some SRTT value. That's nothing but a circular up and down communication. Okay, smooth round trip time. That's, you're sending some packets to the EIGRP neighbor and you're receiving back some acknowledgement. Okay, now what is RTO in that case? RTO is nothing but retransmission timeout. Okay, so in the case of multicast, let's say if the multicast was failed for some reason. Okay, the hello packet multicast was failed some for some reason. Now what your router is going to do is, router is going to send a unicast packet. immediately. Okay, it's going to send a unicast packet, and the other router will send the acknowledgement. Now, this particular movement is called as retransmission. Okay, it happens when there was a drop in the multicast packet, and it has to send a unicast packet and is waiting for the acknowledgement. Okay, so SRTT, RTO, and what is Q count? So basically, this will be always zero. It's nothing but the number of queued EIGR packets. Okay, so let's say from this interface point of view, your EIGRP packets are in queue. Normally that doesn't happen. If your packets are in queue, then your hello packets, that is 5 and 15, will be also in queue, and all your neighbors will start going down because of your hold timer getting expired, right? So basically these will be always zero, but if you see any counts here, that's because your interface is not processing any EIGRP. Might be you have some access list where you are one second. So that could be, might be your ACL or access list is blocking or dropping the packets. Okay, and this is a sequence number. So basically that's nothing but, let's say there was some EIGRP packet sent at the last minute. Let's say there was one more EIGRP packet. So basically the EIGRP packet was sent. So it's just saying the sequence number. So that could have been 14th sequence number between this. Could be 16th sequence number. Okay. Could be 9th sequence number. So it's just a sequence number that they are maintaining. Okay. So from router 7 point of view, what is the sequence number is that we recorded here? Okay, so you will see there is no incremental, because already the routes are being advertised and there is nothing no data is going to uh, be circulated. As we know, the periodic happens only for hello packets. Okay, your routing table will not be in a periodic update. It's only when there is some triggered out. That's why the sequence was happened initially, and now it's just a constant. Until there is some change or something, they are going to be fixed number. Okay, so that's regards to the neighborship table. Now let me show you the topology table. Okay, now here is where you have a few mathematics coming in. Okay, I'll just try to be a little simpler. So let's say in the topology table we have all our backup path. Okay, so from topology table you will see it says it's showing some code. So P is nothing but for passive. Passive is a good example, but active isn't. Okay, if you happen to see A, then that's something you need to be worried about. Passive is good. Okay, so it says from Tokyo 7 to reach 10 dot network. Now where is 10 dot network? That's this. To reach 30 dot network, where is 30? 30 is over here. Okay, uh, to reach 40, where is 40? 40 is here. To reach do we have 20? We have 20. Okay, so you will observe one common thing when you are seeing the EIGRP on the directly connected interface, they show as connected. Agree? Because they are directly connected. Okay, and in this scenario, FD is nothing but feasible distance. Okay, that's nothing but distance between this router to the second router. Okay, how do we calculate? The metric formula. Okay, bandwidth plus delay into 256. Okay, so I have calculated and I have just put up in one of the notepad. So let me just show you quickly how did I get this value, that is 261600. Okay, so on which interface are they actually reading this? It's over on this interface. So I go to show IP, or I can do show interface. Okay, now when I do show interface, I can get the bandwidth. So this is the bandwidth and this is the delay. Delay is in microseconds. Okay, so that's what I have kept it over here. So I have bandwidth and I have delay. Now what I'm going to do is I'm going to first calculate the bandwidth. Okay, so in the case of bandwidth, this is a reference which is 10 to the power 7, and this is my bandwidth, that is 1 2 3 4 4 zeros. Okay, and what is the value that I'm going to get? I'm going to get 1000. Okay, when I just divide the reference bandwidth with my actual bandwidth of the interface, I'm going to get 1000. How to find the delay? Delay is in micron second. Okay, so I just divide by 10. So when I divide this 1000 microsecond by 10, I get the value 100. And how do we calculate metric? It's bandwidth plus delay into 256. Okay, so you just have to add it up. So you have 1000 plus 110. Okay, this is 100, right? So 1000, okay, let me write here 1100 into 256, which is 1100 into 256, and together you have 281600, and that's how you get your metric value, feasible distance or metric value. Okay, so you just have to follow the same process to find the value for every possible distance. Okay, so what is ft? Ft is feasible distance to the neighbor. So if you see this, in this case, this is the ft, and what is the metric? Metric is this. And how do we calculate? The same normal formula that we discussed. Okay, so that's in the case of directly connected. So you will see they have a similar behavior. Okay, because the reason is they all are in a ethernet channel, ethernet link. So that's why they are going to have equal metric towards the similar link. Okay, now regarding to those link where you will see dependency, something in this scenario. Okay, so in this scenario you will see two values. Now these two values have some logic. Okay, so the first value that is 307200, this will be called as ft, that is feasible distance, something very similar to this. And 281600 will be called as advertised distance. Okay, feasible distance, that is the distance from router 1 to your destination. Advertised is from your neighbor to your destination. Okay, that's why you will see it's lesser than your complete ft value. Okay, let me just repeat. Ft, that is feasible distance, your feasible distance is from your R1, R2, R3 and destination. Okay, whereas your advertised distance is from this, starting from this. Okay, let's say R2, R3 and this. So which one should be greater? Your FD will be greater, because that's a total distance which is greater than your AD. Okay, that's why you will see this is greater than this value. Okay, what else can I show you? Okay, I can show you one successor. Okay, why is it showing one successor? Is, do you think there is any alternative path for this connection? There is no alternative path. Okay, they are directly connected or they are directly learned, so there is no alternative path. So that's why it says one successful. Okay, in this case, in the case of 4.4.4, you see two successors. That means there are two possible routes. Okay, so let's see which are that two routes. First of all, where is this 4.4.4? It's over here, which is acting as destination, and I am over here on my source. From source point of view, to reach 4.4, I can see 10.2. 10.2 is this. It's a better route. Okay, I can also see 20.2 is also a better route. So both the equal load sharing is happening. So you see here there is a equal load sharing happening at this moment. Okay, and by default EIGRP will support equal load sharing. Might be in the next class or in the next to next class, I will show you EIGRP unequal cost sharing also. Okay, so that has to be manually enabled. So unequal will be manually configured. Equal by default will start working. Okay, how many links by default? 4 links you can put up over here. So your EIGRP can support 4 different links. Maximum 32 links can be shown up here. Okay, well, that's something over here. I just don't want to put lot of things and make you guys confused. Okay, but before that, I will tell one more thing, that is about this link. Okay, it's called as stuck in active, which can be asked either in interview or either in uh, uh, might be in the certification. Okay, so S, a small s or a lowercase s, is called as SIA status, which is stuck in active. Now this is a scenario when EIGRP has not received a reply to the query packet. Okay, so basically there will be 3 minutes allotment for that. Okay, there will be 3 minutes of allotment. Let's say router 1 sent a packet to router 2, not any packet, not your hello packet or what, not about other packet I'm talking about. It's the query packet that I'm talking about. Okay, so your router 1 sent a query packet towards router 2. There was no reply. It's going to wait for 3 minutes, and that scenario is called as stuck in active. Okay, this is a scenario when your primary route was down and now it sent the query packet to find the backup link, but the backup link is not known to us. That's why it said that 3 minutes of window. Okay, so that's the case when you don't have any possible route to reach the destination. So that scenario is called as stuck in active. And if you remember, anything having in active is not a good example. Okay, passive is good. Passive is something which says packet flow, but a resembles it's not good. So stuck in active is something which is not a good example in your topology. Your primary link is already down, and now you are sending the query packet to get the backup link, but the backup link is unknown to you guys or your router. Okay, so that's the case when it's called as stuck in active. So that was regards to EIGRP topology. Let me show you routing table now, the best route that's getting placed here. Okay, so from the routing point of view, the routing table point of view, what is D here? D is nothing but EIGRP. Okay, so you might be still wondering why they used D instead of EIGRP. Why not E? Because in case of OSPF, we make use of O. In case of BGP, we make use of B. In case of RIP, we use R. But in case of EIGRP, we don't use E. The reason is there should be some uh, E used for some other purpose. Like for example, this is used. Okay, and there should be some protocol which was already denoted with the alphabet E. That's why, in order to not have any confusion, what they did is they just came up with a new alphabet D. That's why EIGRP has this irrelevant kind of protocol code. So if you see D, then that's a EIGRP connection. Okay. So in this topology, we have the EIGRP routes, and if you see for the destination 4.4, you have two best equal routes. The first one, the 90, is nothing but the AD value. This is the metric value. Okay, and the rest of thing, that is 30.1. Where is 30? 30 is here. 50 is here. Where is 60? 60 is here. So that's nothing but that's your EIGRP routes, and this is the metric to reach to this network. Okay, so one hop next, you have your destination, that is your 4 dot. So the additional thing will get added up, and that's why it's incremental. Okay, So from routing table point of view, nothing much over here. So D represent EIGRP, it's represent the destination prefix with prefix length of 24. This is the AD value, this is the metric to reach the to reach the destination. This is the interface via where the routes are being sent, so the local interface. Okay, so 10.2, okay, 10.2, that's this router, the next hop. Okay, these are nothing but the next hop gateway. So to reach 30.2, you have to go towards 10.2. To reach 50.1, you have to go towards 40.2. To reach 60 network, you have to go towards 20.2. So that's the next hop gateway IPs. These are its own interface IP. Okay, the outbound interface. So let's say from this router point of view, this is the outbound interface. Okay, so you have the outbound interface. And what are these timers? The timers are nothing but the time since the route was learned. Okay, the time since the route was learned. That's something which is mentioned here. So we learned the three tables and the three different parameters. Okay, so let me quickly check if I have something pending for today. I guess we are done, and the next things will be taken up in the next class. Okay, like summarization, the path manipulation. Okay. Yep. Next, the other things we have covered today. Okay. Fine. So I'll just let you guys to have Q&A in case you guys have any doubt. So you can ask me. Okay. So let me quickly go through this. Okay, so GLBP multicast was not 10, it was 2 and 102 if I'm not wrong. Okay, where's my pointer? Okay, so in case of multicast, it's your HSRP which had dot 2 and HSRP version 2 GLBP, these had dot 102. Okay. Okay, so what else do we have here? Okay, T circuits are some WAN circuits. Okay, the WAN circuit where the bandwidth are higher, like your 10 giga Ethernet ports, not your normal Ethernet or a LAN ports. Okay, T circuits, they are called as T circuits, T1 circuits. Yes, that's into 3. Okay, so if let's say you have hello timer as 10, your whole timer will be into 3. That's a best practice, but yes, they are customizable. You can change them. Okay, the best practice is into 3 in case of EIGRP. Additional configuration required for EIGRP 0 and EIGRP 1. I didn't get this question.
Yeah,
Might
Sagar.
be if you rephrase, I can
Yeah, it
explain you.
means we
Yes.
have the two router. One is existing router. The version is 11.1. You mean EIGRP version 0? The existing router version is okay.
Okay. Okay. They are not backward compatible. So that will be an issue in case of 0 and 1. That will be an issue. But yes, one more thing, these are very outdated codes. Okay, the software codes are very outdated. So I don't think you will see any such chances of seeing two versions in one router. Okay, nowadays they are only one, just a one version. There will be no two versions. Okay. If both route is same bandwidth and delay, then who will elect? That we checked. So if there is a same bandwidth and delay, your EIGRP is going to put both of them in the routing table. So basically it will by default select 4, but you can keep up to 32 also. Okay, yes, that's called load balance. Yes. As I told, successor is nothing but one route towards the destination. If you have two ways to reach the destination, you will see two successor. Okay, they are also called as feasible successor. Feasible successor is a backup. Okay, so backup for your primary route. 29 router, which is 29, is that the center one? Okay, so in this scenario, I mean, in this case, so let's say the 4.4.4, it had two best route. Okay, so the reason why it has not selected is something which we need to check. Okay, so I'll tell you in the next class why is it not checked. It's not about the highest IP, or it's not about uh, what do you say, about the criterias here. Okay, bandwidth or delay. So I'll tell you why this is not selected and in which scenarios that will get selected. Yeah, that's right. It's because of the dual algorithm. Okay, so your best two will be getting selected. Okay, so that was regards to the chat window. So do you guys have any other doubts regards to the class we had today? Okay, so in that case, I take it as no, and we will meet up in the next class. Okay, great. Fine, guys. So let's meet up in the next class. Have a wonderful day ahead. See you in the next class. See you, everyone.